Hi, my name is Alyssa Cabello, and I'm doing the original problem portion of my presentation over Newton's law of universal gravitation. My original problem states that two objects are floating in space. We have object A that has a mass of 8.0 times 10 to the fourth power kilograms, and then we have object B, it has a mass of 2.5 times 10 to the fifth power of kilograms. And the distance between their centers is 3.0 times 10 to the second power meters. So what is the gravitational force between the two objects is what my problem is asking. So later on we'll get into it, but you'll see how, this mass, this distance between their centers, it'll all come together into a equation that you may or may not be familiar with. So the relevance of the question to this topic, and this question applies Newton's law of universal gravitation together with centripetal force, showing how gravity is responsible for orbital motion. It connects two major physics concepts into one problem. So this question is important because it shows how gravity isn't just a theory, it actually explains motion. Even though the problem looks simple, it represents how real objects in space interact. The benefits of understanding the original problem that I created. Understanding this problem helps explain how satellites, planets, and moons stay in orbit. It also straightens skills in combining multiple formulas, working with circular motion, and solving multi-step physics problems. So this type of problem helps build problem-solving skills because it requires multiple steps. So you have to make sure you do your math right, fact check it, make sure you follow order of operations or whatever the case may be. Learning how powers work if you multiply or divide, whatever my problem is going to ask for. It also helps understand how scientists predict motion without actually being in space, so that's very important. For example, NASA uses these same principles when launching satellites. So learning this isn't just for class, it has real applications. The process of writing this question outlined, I began with the relationship between the gravitational force and centripetal force. Then I selected realistic values for a planet and a satellite, which, these could be a planet, whatever. Instead of giving the distance directly, I included the orbital period, which requires finding velocity first before solving for the radius. This adds multiple steps and increases the difficulty. So I didn't want to make a basic plug-in problem, so I made it a little more complex. I chose values that would require multiple steps instead of just one formula. This forces you to actually understand the relationship between the variables. It also reflects how real physics problems are rarely straightforward, which we have seen a couple of those in our practice problems in class. So the uniqueness of questions discussed. This problem is unique because it does not directly give force or distance. Instead, it requires combining equations and introducing an orbital period, making it more complex than a standard gravitational force problem. What makes this problem different is that it requires deeper thinking. So you can't just immediately solve it, you have to break it down step by step. This is more like real scientific problem solving. It basically tests your understanding, and it's not just like you memorizing how to plug in something in formula and solving it. So here's a diagram that I provided. It is a picture that helps visualize what's happening between the two objects. Instead of just numbers, we can actually see the distance and interaction. And visuals are important in physics because they help connect equations to real situations. So the formula that is relevant to this problem I created is the formula that you use to solve gravitational force, which is right here. Gravitational force equals gravity times mass 1 times mass 2 over the distance between the centers of the objects squared. So, like, I kind of just explained all these constants, what they mean, but F being the gravitational force, G being the universal gravitational constant, which is 6.67 times 10 to the negative 11th power newtons times meters squared divided by kilograms squared. And then mass 1, M1 and M2, those are the masses of the two objects in the formula. And then R equals the distance between the centers of the objects, and it's going to be squared. This formula shows that the force increases with larger masses and decreases as the distance between them increases. Understanding how each variable affects the force is key before plugging in numbers. It's very important to know how, if a certain variable is higher or lower, whether it's, R or a mass, how it would affect your entire equation before you even solve it, because sometimes you can know, like, oh, if this number's higher and then that's the distance, it's going to decrease my gravitational force. Usually, it follows the same, it does follow the same rules that are applied. But this formula shows a relationship, so it's not just numbers. As, for example, the mass increases, the force increases. So that's a direct relationship. Distance has a bigger effect because it's squared, and that means small changes in distance have a huge impact on force. So this is why planets far away feel less gravitational pull. So I am going to walk you through the solving process for my problem. So first, I'm going to organize my known values so I don't make mistakes. So we have set them here with their standard SI units as well. So kilograms for mass, meters for distance. So we have, our mass 1 that we discussed is 8.0 times 10 to the 4th kilograms. And then we have our mass 2 plugged in there, 2.5 times 10 to the 5th power kilogram. And then we have our R plugged in here, which is our 3.0 times 10 to the 2nd power meters. And then we have our gravitational constant, which is 6.674 times 10, so forth. I'm going to multiply the coefficients first and handle the powers of 10 separately next. That's our step 2. Scientific notation is important here because the numbers are very large. So that means you would do 8 times 2.5, which gives you 20. And then you do 10 to the 4th power times 10 to the 5th power. If you remember correctly, the rules of multiplying something to the power means that you are just adding. So really, we're just adding 4 plus 5, which would be 9. So then you will get 10 to the 9th power. So now we're going to continue and square the distance for step 3. So I have the distance of 3.0 times 10 to the 2nd power, which is just going to equal 9 times 10 to the 4th power. So now, step 4, we're going to substitute into the formula. So we're going to plug it in here. F equals 6.674 times 10 to the negative 11th, multiplied by 2 times 10 to the 10th power over 9 times 10 to the 5th power. So let's simplify this fraction. So I got 2.22 times 10 to the 5th power. So to walk you through that process, basically you're going to divide these coefficients, and it's going to give you approximately 0.2222. And then when you divide powers with the same base, you just subtract the bottom exponent from the top one. So you're going to do 10 minus 4, which gives you 10 to the 6th power. So you would be getting your 0.222 times 10 to the 6th power. And it's not completely simplified because we need it to put it in standard scientific notation, and we need one non-zero digit before the decimal point. So we can move the decimal one place to the right, which means we decrease the exponent by 1. So it leaves you with 2.222 times 10 to the 5th power. And that's rounded to their right amount of significant figures as well, which is 3. So now we're going to go to step 5, and we're going to multiply by g. So 6.674 times 10 to the negative 11th power times 2.22 times 10 to the 5th power. So let's start with multiplying the coefficients here. So we're going to do 6.674 times 2.22, which is approximately 14.82. And then we're going to add the exponents here because we're multiplying them again. So 10 to the negative 11 times 10 to the 5th power, which really is just negative 11 plus 5, which will give you 10 to the negative 6th power. So F approximately equals 14.82 times 10 to the negative 6th power of newtons. So let's normalize this number. We can rewrite 14.82 as 1.482 times 10 to the 1st power. And we can combine the powers of 10. So let's multiply the powers of 10 and add exponents. So we're going to combine these powers of 10 here. And when you multiply powers of 10, you add the exponents, as we've done multiple times in this equation. So 10 to the negative 1 power times 10 to the negative 6 power is negative 5. So now we have F equals 1.482 times 10 to the negative 5th power of newtons. And our final rounding, which is 2 significant figures, is going to be 1.5 times 10 to the negative 5th power of newtons for our gravitational force. So my final answer is the gravitational force between the two objects is approximately 1.5 times 10 to the negative 5th power of newtons. I converted to the proper scientific notation so the answer can be standardized, as you can see at the end. So with my solution being correct, I checked all out the units that they're in the correct SI units, and that's necessary for accuracy. The answer makes sense because the force is relatively small, and that is expected for gravity. Gravity is a weak force, so we shouldn't expect a large number. And the solution is correct and applies to the Newton's law of universal gravitation. The gravitational constant is used properly, and the order of operations is followed correctly. Scientific notation is handled accurately throughout the steps. The problem correctly fits the concept of finding gravitational force between two masses in space. And the final answer is also rounded to 2 significant figures, matching the precision of the given values. The additional valuable information that is provided. One important idea to understand is that gravity acts between all objects with mass, not just planets. Even small objects still exert gravitational forces on each other, but those forces are usually too small to notice. Another key point is that gravity depends heavily on distance. So if the distance between two objects double, the force becomes 4 times weaker. So this inverse square relationship explains why gravity behaves so differently over large distances, like in space. many people think gravity only applies to planets, but it actually applies to everything. We don't notice it between small objects because the force is just weak. It's like extremely weak. The universe square law is one of the most important ideas here. It explains why gravity drops off so quickly over distance. So, some of my additional interest was one part of the topic that I found interesting is how Newton's law of gravitational can explain the motion of planets and satellites, because when you think about it, you're like, oh, you know, they're just floating in space, but no, they have gravity to other things to, you know, to keep them there. Or the like the relationship between each other. But it's interesting that the same equation we use in basic problems can also describe how objects orbit Earth or how larger systems in space interact. It's interesting that something we learn in class is actually used in space missions. I'm also interested in how this concept connects to real world careers like aerospace engineering or astrophysics. In those fields, having a strong understanding of gravity is essential for designing systems and predicting motion. Like all the, you know, things that go up in space, they kind of have to think, you know, how is this going to act like, you know, in gravity with zero gravity. But yeah, this topic connects math, science, real life applications. It made me realize how important physics is in real world careers. You you think, you know, physics is just this hard prereq you have to take, but it really opened my eyes up to see, you know, how physics has a lot to do with things that we're doing. Just, you know, me sitting in this chair, I'm stuck to here because of the gravity on the Earth. So, my overall summary, Newton's law of universal gravitation explains how and why objects attract each other based on their masses and the distance between them. Throughout this project, we applied the formula, we interpreted variables, and we worked through different types of problems. These steps help build a clear understanding of how gravitational forces work in both simple and more complex situations. This topic is important because it provides a foundation for more advanced physics concepts and explains real-world phenomena like planetary motion. Overall, this project helped me understand how gravity works mathematically and the concepts. I learned how mass and distance affect force in a predictable way. This law connects motion on Earth to motion in space. It's a foundational concept that leads into more advanced physics topics. So here's the most relevant source for me that I found useful in this topic and very accurate, because it is our OpenStax textbook for the physics course, and it's just the portion going over Newton's universal law of gravitation. It was used more frequently than any other source and provides a wide range of information related to the law. It was super helpful because it explained both the formula and real world applications. And it also provided examples that helped reinforce my understanding. And just using a reliable source like this physics textbook made the information more accurate. And that is the end of my presentation on the original poem I created for Newton's law of universal gravitation.